Hey, this is Horner. We're going to look at 18.3. This is the microscopic view of current in a metal, and we call this the free electron model. The electrons here have what we call a non-zero average velocity, and it's basically just termed the drift velocity. So electrons in a wire really are not flying from one side to the other. Okay, they're drifting from one side of the other to the wire. So really, what they're doing is they're just transferring that energy from one place to the other in the wire. That tends to happen in a net direction, going from the negative side or the low potential to the high potential side of the battery. Um, and so the electric field obviously is traveling in the other direction as is the current. So the magnitude of this drift or velocity is a lot smaller than the instantaneous speed of the electrons. So they're kind of jarting around all like this, but overall their drift velocity is very small. So they're going really far to go very, very small distances. So you'll notice that they're traveling this huge amount of, I guess you could think of it as, remember the difference between distance and displacement. So the distance here is great, but the displacement is only from here to here. Same thing, the distance that they go is great. So this distance is huge, but the displacement's very small. So we call this displacement a drift velocity, is essentially what you're thinking of here. So there are lots of collisions here. It's got uniform acceleration because of those collisions. Every collision between that electron and an ion has a little bit more kinetic energy that it can transfer to that ion. So we know that this drift velocity is constant, and the energy is transferred from the electrons to the ions at a constant rate, and we end up seeing more of this current as it flows through. So here's the big relationship between current and drift velocity. There's an equation that we can use, and it says the number of electrons in the volume is N is equal to, so this is the number of electrons is equal to little n times capital A times Vd, which is the drift velocity, times the change in time. So our V delta T is just this velocity times time, so that's a distance, is a velocity times time. We've got so many numbers of electrons in this certain area. So the magnitude of the charge, if you want to calculate the change in the charge, is just N, capital N, so that's this whole thing, times the charge on an electron. So all they did is they took this equation and they plugged in the charge of an electron right here. And that's essentially how you would find the charge. So we'll do kind of a problem similar to that. We can go on and just say that the change in charge is equal to N times E, which is NE AV dt times delta T, and therefore the magnitude of the current in a wire is equal to I, which is equal to Q over T. So we've already learned about this equation. That's the I quit equation. And that's equal to the number times the charge on an electron times the area that they travel through times that drift velocity. So electrons carry negative charge. The direction of the current flow is opposite to the electrons. So if the electrons are traveling in this direction, we know that our current flow, so our current is flowing in the exact opposite direction, which should be in the direction of the electric field of that wire. The equation I is equal to Q over T is equal to NeAVD. We can generalize this. The current carriers don't have to be electrons. We can just replace the E with any of the charge carriers that you have. So you'll see here's a positive charge carrier, here's a negative charge carrier, and these quantities are the drift speeds of those different charge carriers. So it can get really complicated. We'll try to keep it as easy as we can. Example 18.2, we have a 12 gauge copper wire, and it's commonly used in household wiring. It's got a diameter of about 2 millimeters, and there's about 8 times 10 to the 8th, 28th conduction electrons per cubic meter, and that's pretty high. Copper is a great conductor of electricity. So if the wire carries a constant DC circuit of about 5 amps, they want to know what's the drift speed of the electrons. First thing we need to do here is find the area. So area is equal to pi r squared. You can also say that that's 1/4 pi d squared. So here's our equation. The drift velocity is equal to I. Remember, I is the current, and that's over N, the number of electrons, times the charge on electron times the area. So we've got 5 amps because for all that's not area, that's just amps. This is the number of electrons per that cubic meter. Here we've got the charge on an electron. We've got 1/4 pi times, and then here's our diameter that we have squared, so we're actually using this area equation. Now we're going to end up with 1.179 times 10 to the 4th meters per second, and that's really about 0.118 millimeters per second. So obviously it's not a very fast speed at all. For 18.4, this is about resistance and resistivity. So we'll do a lab where we play with Play-Doh, and you're able to find out the resistivity of Play-Doh. And we do that by measuring current, voltage, finding the resistance, and then using an equation to find that resistivity. So many conductors, we know that the current is proportional to the change in voltage. And so we now can kind of start to put together Ohm's law, where current is proportional to that change in change in potential. So Ohm's law is really not a universal law of physics like a lot of other laws, like the conservation laws, for example. It does not apply to at all to some of the materials. Some of them do obey Ohm's law, and some others really do not. And that's especially if your change in potential becomes really, really big, so you don't see it. So here we're going to say any homogeneous, so that's just made out of one material, follows Ohm's law for some range of potential differences. So metals are really good conductors. They follow Ohm's law over a wide range. So we typically want to do this with metals. We don't want to do this with nonmetals. Electrical resistance is defined as the ratio of the potential difference divided by the current. So how much potential difference there is going as a comparison to the current there. So in SI units, it's going to be an ohm for resistance, and that's basically just a volt per amp. An ohmic conductor, so one that does follow Ohm's law, has resistance that's constant, okay, so regardless of the amount of potential you put in it. And when we do that, the graph of current versus potential difference is a straight line, and the slope is really 1 over the resistance. So for some systems that are non-ohmic, so that don't follow Ohm's law, the graph of the current versus the potential difference is really not linear at all, and so they call it dramatically nonlinear. So here's a ohmic resistor. You'll notice that the resistance is the same regardless of the amount of volts, and we're measuring current per change in potential, and this is a very straight line. So that's an ohmic resistor. This is one that would be non-ohmic, so it comes up, kind of flattens out a little bit, and then we get a little bit higher and you get to the point where it's no longer ohmic. So here it might be ohmic, here definitely is not, and then takes off again. Here's another one where you can kind of see what's going on. We've got a really high resistance at about this voltage. And then as we increase the voltage, you'll see that that resistance continues to go down. Resistivity, in the Play-Doh lab, we've seen that R is equal to the resistivity times the length over the area where R is resistance. And this just assumes that there's a uniform distribution of current across the cross-section of the conductor. The constant proportionality, okay, is that resistivity that we looked at before, and the unit for resistivity is an ohm times a meter. The inverse of that is called conductivity, and that's how well something conducts electricity. Here are some resistances and resistivities of different materials. And so you'll see silver, copper, gold. You'll notice that gold is pretty high. Iron, here we've got platinum, nichrome wire, pretty high in terms of resistivity. Semiconductors, silicon, 2300, okay? So this one's pretty high comparatively. These have a very low resistance, the ones down on the bottom. Insulators, extremely high resistance, and you would expect that. So silver is probably one of your best conductors. Copper is, gold is. Copper is pretty plentiful, silver and gold are not, but they all have properties that kind of help a little bit. Resistivity of water. Pure water contains only ions, just of hydrogen and hydroxide. So pure water is an insulator. But if I put a little bit of salt or any other mineral into the into that wonderful material called water, then it lowers the resistivity and it becomes less resistive. So if you have water that has lots of impurities, you can really measure using those impurities, using the resistivity, how pure that water is. So the more electricity it can conduct, probably the worse the water is. In example 18.3, here we've got a 30-meter long extension cord. It's made from two 19-gauge copper wires. They want to know what is the resistance of each wire at 20 degrees, and the diameter is about 0.912 millimeters. Then they want us to see what happens when I replace it with aluminum wire. So for this first one, we've got copper wire. We found the resistivity of copper is 1.67 times 10 to the negative 8th ohm meters. We found the area using the equation you've seen here. And then we're going to find the resistance, so we plug in the resistivity, the length of the wire, and then that cross-sectional area. We end up with about 0.767 ohms, so that's for the copper. So here what we're doing is we're looking at the resistance of aluminum, and we know that it is a lot less than the resistance of copper. And so we're going to put in our resistivities. Okay, so here's our resistivities. We notice that we can cross off the 1/4 pi. We can also cross off the length, and now we're left with the resistivity of aluminum times the diameter of copper here. And that should be less than the resistivity of copper times the diameter of the aluminum wire. We want to look at the diameter of that aluminum wire and compare it. So we go ahead and we're going to use the copper. So that was 0.912. It's times, here's the resistivity of aluminum divided by the resistivity of copper, and we end up with about 1.15 millimeters. So you would need a 1.15 millimeter aluminum wire to match that 0.912 copper wire, so that their resistivities are in line with each other. Resistivity does depend on temperature. It doesn't really depend on size or shape of the material, but the warmer it is, typically that changes it. So a couple of primary factors here: the number of conduction electrons and the rate of the collision. So at a higher temperature, there's more internal energy in the wire, and those ions vibrate with a really pretty big amplitude. And as the result, those electrons collide a lot more frequency. So with less time to accelerate between collisions, they get smaller drift speeds and the current is smaller. So as the temperature goes up, the resistivity increases. It's just harder to get any more energy through it, since a lot of that energy is being absorbed because of heat. So a lot of materials, the relation between resistivity and temperature is linear over a pretty wide range of temperatures, so about 500 degrees Celsius. So here we've got the resistivity is equal to the original resistivity times the quantity 1 plus, and then we've got a quantity alpha times delta T. So we said rho naught, so this is rho. This is a little symbol called naught, and that's the resistivity at a temperature, original temperature. And then resistivity is the resistivity at this new temperature. Okay, this really should be alpha. So the quantity alpha is called the temperature coefficient of resistivity, and it's got units of 1 over Celsius or 1 over Kelvin, depending on which one you want to use. If you remember the chart that we were looking at earlier, we didn't really talk about the alpha values, but now we can go back and kind of look at those alpha values again. So we're going to go back here, and here are our alpha values, and these are in per degree Celsius. So you'll see that silver is about 3.8 times 10 to the third, and then they kind of change a little bit as we get through here. You'll notice there aren't any for insulators, but we do have some for carbon, germanium, and silicon, which are all semiconductors. So let's go ahead and move back to where we were. And we can kind of go on. Here we've got a nichrome wire. It's a heating element of a toaster. And it has a resistance of 12 ohms when it's red hot. So when it's about 1200 degrees Celsius, it doesn't have much resistance. They want to know what's the resistance of the element when it goes back down to room temperature. So after you take your toast out of the toaster, after you put bread in. And they want us to ignore changes in length or diameter of the wire. So our strategy here, since we assume the length and cross-sectional area are the same, the resistances of the two temperatures are proportional to the resistivities. So we can just say that resistance 1 over the original resistance should be proportional to the resistivity over the original resistivity, so the new one at the higher temperature over the original. So if we do that, we're going to end up with R over R naught, and that's just rho L over A, and then rho naught L over A. So these, we can cross off the L over A's, and we're left with rho over rho naught, which we know is 1, plus alpha, so that's that value that we can look up in the table times the change in temperature. Our change in temperature is from 1200 degrees Celsius to 20, so we get about 1180. The alpha value for nichrome is about 0.4 times 10 negative third. And now we can plug everything in and find out the resistance. So here, resistance is equal to, that's the original, so that's at the 20 degrees. At the higher temperature, we said it was 12. Then we've got 1 over alpha times that temperature change. And we find out that it's about 8 ohms. So it does change as it gets hot. We do know a resistor. We've looked at resistors. They're designed to have a known resistance, so they've got these color bands on them, so we can find out what that resistance is. In a circuit analysis, we can say that voltage is equal to current times resistance, and remember that voltage actually is the potential difference between the two ends of the resistor. And so even though we got rid of the delta sign, that's still the same. The symbol for a resistor is the squiggly line. It looks like that. If I have a straight line, this is a wire, and it has very low resistance. And so remember, when we measure the voltage across a resistor, it does give a pretty big voltage compared to the battery. It should be just a portion of the battery, but it shouldn't be very, very small like a wire would be. And we call that a voltage drop. This is the internal resistance of a battery. So batteries do have a little bit of resistance between the two poles or between the two potential ends. And so you can actually measure that as you go through it and find out what it is. When the current through the source of that battery or that has an electromagnetic force is 0, the terminal voltage, that's the potential difference between its terminals, is equal to the EMF. But when the source supplies current to a load, like a light bulb or toaster or anything else, its terminal voltage is usually less than the EMF. So there's your EMF, and this is your terminal voltage. So if the current I and the internal resistance is R, we have to subtract that from our original EMF, and then that gives us our voltage in the actual battery. So this is where batteries with those internal resistors really don't put out as much potential difference as those that don't have these internal resistors. And that is the end of the section. The next thing we'll talk about are Kirchhoff's rules.